Solar radiation is just the scientific word for sunlight. And I should not be surprising you when I say that, crops need sunlight to grow. All right, so in general, on average, more sunlight equals more crop growth. And that goes right back to our yield equation where technically it's not total sunlight, it's how much sunlight is intercepted by that crop canopy. But there's a pretty direct relationship between solar radiation and crop yield. Here's a figure from a scientific paper that shows this relationship, really beautifully. So this is from Hawaii, where corn can be grown year-round. Again, they never have frost. They have a 365-day frost-free period. And so what you see here on the x-axis is average solar radiation on a daily basis, and on the y-axis is corn grain yield. And you can see a very strong linear relationship. So, more sunlight, more yield. Daily solar radiation depends on two factors. First is the intensity of solar radiation, so the amount of energy that's hitting a piece of land, a meter squared on a daily basis. And that is dependent on things like latitude and cloud cover. On a typical cloudy day, solar radiation is about half of what is achieved on a cloudless day. We also have the duration of solar radiation during that day. In other words, how long the sun is in the sky for. And longer days obviously tend to have more solar energy calculated on a daily basis. Generally, solar radiation, again measured on a per area basis, declines as you get further away from the equator. And this is just basic geometry that, the intensity of that sunlight is going to decline because it's spread out over a larger area that sunlight is. This is a graph that tracks solar radiation intensity in terms of watts of radiation per meter squared at different cities that are at different latitudes. And you can see it varies quite a bit throughout the year, but also on a given day of the year, it'll vary quite a bit across latitudes. Here's a map that shows daily and yearly irradiance across the globe, and just have a look at Canada and see what color that is compared to, say, the southern United States or many parts of sub-Saharan Africa. So daily solar radiation is dependent on the intensity, what we just talked about, and also the duration of solar radiation, essentially day length or photoperiod. So this is a slide you've definitely seen in some of my previous videos, and Dr. McAuliffe, I'm pretty sure, touched on this as well. Essentially, day length varies throughout the year, reaches the longest day of the year is June 26th, the shortest day is in December, and in the equator, photoperiod varies very little. It's about 12-hour days, but as we go further north or further south, the longest day of the year gets longer and longer. Now, photoperiod does two things that affect crop productivity. First is a direct effect on crop growth, and that's via that yield equation. Just the longer the day is, the more sunlight's pounding down on that crop, and the more biomass that crop can accumulate. Again, going back to that yield equation. But day length has an indirect effect on crop productivity because it also modifies development. Right? And I know Dr. McAuliffe covered this earlier. Some crops and many temperate crops are sensitive to photoperiod. So development will either slow down or speed up depending on the length of the day. What this means for crop productivity is that photoperiod is going to influence, for example, the duration of grain fill or the duration of vegetative development, and in that way will indirectly influence yields. This is an example from Australia using canola that illustrates the power of photoperiod or day length on crop phenology development. So here these scientists planted canola 3 different dates, and they did it to ensure that at flowering each planting date would experience a different photoperiod, either 11-hour days, 12 hours, or 13-hour days. And you can look at the column days to flowering. Okay, you're basically halving the number of days to get to flowering if you increase day length from 11 to 13 hours. And it's similar if you count not in calendar days, but in thermal time, degree days. So photoperiod, on one hand, increasing the day length from 11 to 13 hours, you have 2 more hours of sunlight. That's great. That's more potential photosynthesis, but you're having the time to flowering. And so vegetative development might be happening too early in this case. And that might be, vegetative development is stopping too early in this case. And you might have lower yields because of that. Perhaps there's lower leaf area index, lower interception of that radiation. So overall, there's this trade-off between day length and how it benefits total potential photosynthesis and how it influences development. The last thing I'll point out is that canola is flowering sooner as the day gets longer, and so canola would be considered a long day plant. Soybean, which is a short day plant, would actually take longer to flower as day length increases. Some of you might know who Luke Bryan is. He's a famous country singer, and he also moonlights as an agronomist. And he's famous for this saying that rain makes corn. And in his song, he talks about how corn makes whiskey. But let's in this video focus on the first part of that statement, that rain makes corn. Is Luke Bryan correct? In most temperate environments, you can have days with a lot of rain or days with a lot of sun, but you don't have both, right? Cloudy days are rainy days, and sunny days aren't very rainy. This is not true in some tropical environments where you have monsoon rains, which, you get a lot of rain in a short amount of time, say in an hour, and then it's sunny the rest of the day. In temperate environments, you either get one or the other. And this leads to the development or the potential development of this trade-off between solar radiation and rainfall. And both are important, but maybe there's a trade-off there that we need to maybe think about a little. This is a table that has data from the Aurora Research Station on corn grain yields over a 10-year period. And we measured both rainfall and total photosynthetically active radiation from a nearby weather station like a kilometer away from the field. And then we summed up total rainfall and photosynthetically active radiation that occurred during different growth stages. And we attempted to correlate rainfall and radiation during these growth stages to final grain yield. And I'm just showing you two different growth stages, but we did a bunch more. So during the V5 to V12 growth stages, that's roughly mid-June to mid-July for Aurora, rainfall during this period was very positively correlated to grain yield. But photosynthetically active radiation during this time was negatively correlated to grain yield. If we went a bit later in the season from VT or tasseling to the R2 stage of corn development, there was no significant relationship between rainfall during these growth stages and corn grain yield, right? A non-significant correlation, but photosynthetically active radiation between VT and R2 was significantly and positively correlated to grain yield. So what are we to make of these data, right? Is it true that more sunlight during V5 to V12 reduces grain yield, right? No, that would go against the yield equation. And then, if the yield equation isn't true, then nothing we know about crop science is true. What's probably going on, as I mentioned earlier, is this negative inverse relationship between rainfall and accumulation of photosynthetically active radiation. In other words, sunny days are not rainy days, and rainy days are not sunny days. And it seems like, at least at Aurora, in this soil texture, in this crop management system, the details of which I won't bother you with because they're not that important for this video, during the V5 to V12 growth stage, it seems like rainfall is more important than solar radiation, whereas during the VT to R2 growth stage, solar radiation during that development time is much more important than rainfall. All right, so we have this inverse relationship between rainfall and sunlight. Put simply, very sunny days are not rainy and very rainy days are not sunny. But we also have a positive relationship between sunlight and temperature. In other words, sunny days are typically warmer days, and colder days are typically not sunny. From earlier lectures with Dr. McAuliffe, we know that temperature has a huge impact on crop development, and so sunnier days can be warmer days, and they might speed up crop development, and that may or may not be a good thing for overall crop productivity. This is an example that we'll go through using real-world data from both Ontario and New Zealand, two different temperate agricultural regions. So the wheat rainfall period is about 660 degree days in both New Zealand and Ontario. And let's go through some other environmental variables to understand, what is limiting yield potential in both of these environments. So during grain fill, that's after pollination, daily radiation in New Zealand and Ontario are very similar, but it's a little bit higher in Ontario. Our days are a little bit warmer and a little bit sunnier. Now, because just based on radiation, just based on that yield equation, because daily radiation is a little bit greater in Ontario, potential daily grain yield is a little bit higher as well. This next row shows us the duration of grain fill from pollination to maturity in calendar days. And on average in New Zealand, it's 40 days, in Ontario, it's 34 days. Now keep in mind the growing degree day requirements for grain fill, 660 degree days. It's the same in both of these locations, but it's much warmer in Ontario on average, and so you accumulate heat more rapidly in Ontario, thus less number of calendar days required to reach maturity compared to New Zealand. So on balance, when we do up all the math, basically the duration of grain fill multiplied by the potential daily grain yield gain, potential yield is about 2 tons per hectare higher in New Zealand compared to Ontario. And that is not to do with the total intensity of daily radiation. It's higher in Ontario, but it has to do with the duration of grain fill. And so, again, we can have sunnier days. That can increase yield because of more PAR. But if it increases total temperature, right, if it makes those days hotter, then we might cycle through developmental phases faster, which will reduce yield. And that's what's going on here when we compare Ontario to New Zealand in terms of wheat. Most temperate areas have a pretty dramatic fluctuation in day length over the growing season. For example, in Ontario, Southern Ontario has about a 2-hour difference in day length between June and the end of August. So from a management and genotype perspective, you want to take advantage of those longer days by having crops that close their canopy early and by planting early as well, right? Earlier planting results in quicker canopy closure, being able to take advantage of those longer days that only grow shorter after, the end of June. One management practice that has been heavily researched in Ontario is the practice of frost seeding spring cereals. You're essentially seeding cereals not at the end of April or early May when they're normally sown, but much earlier when there's actually the soil is almost frozen, just barely above freezing. And the idea here is that you're seeding earlier, and as a result, that crop is going to reach flowering earlier. Development will be quicker than if it was planted in April or May. And so you're going to have grain fill much earlier in the season than you normally would when the days are longer, right? Because we have longer day lengths, and also cooler. So the grain fill period actually lasts longer, going back to that New Zealand example, because we want to try to avoid as much as possible those really hot days in July where development is quicker and then we lose out on grain fill. So on average, this is a 23% increase in yield. This is a value that was done multiple years, multiple locations in Ontario. So the benefits of frost seeding spring cereals are quite significant. And again, it's because that development's happening in more favorable growing conditions when days are longer and cooler. So frost seeding is difficult to pull off. The weather conditions have to be just right. It takes quite a bit of effort on the part of the farmer to be able to successfully frost seed, but the yield benefits are certainly there.